Now, it turns out, some of you may be thinking, that if we take our magnetic field, everyone knows what these scanners look like. These tubes that I'm drawing where the patient goes inside, does everyone know what I mean by that? I think so, right? Okay, so we take our patient and we put him in here. And one of the things that might have crossed somebody's mind is, so we turn on an externally applied magnetic field. Let's say it's 1.5 Tesla. That's a common field strength. So we know by experiment that at 1.5 Tesla with a static magnetic field strength, meaning it's in that orientation, doesn't change, that we generate some amount of magnetization in the patient that has an orientation exactly the same, it's in the same line as the applied magnetic field. We don't generate any tilt of that magnetization. And even if we go and we ratchet this up, right? Let's say we go up to 11 Tesla. In Ohio, there's an 11T scanner that you can put a human being in. So, or even if we go even higher, there are these vertical bore things. Some of you that have done biochemistry, anyone ever here do NMR in a biochemistry lab? No? Yes, no, where you put a little test tube of a sample in there. So those could be quite high field strengths. Maybe they'll be 21 Tesla. They're very strong magnetic fields. But you never generate any amount of change in the orientation of the magnetic field. You are adding additional energy to the system, right? The greater the magnitude of that applied magnetic field, it's more energy being put into the system, but it's never sufficient to cause this change in orientation. And the way that we do that is, we've talked about nuclear magnetism. So the R in NMR, this is what it used to be called, by the way. Does everyone know why there are no NMR scanners?
Nuclear was not.
Yeah, the term nuclear was determined, I think this was mostly General Electric, determined through market research that calling anything nuclear was not good for sales. So that's why we have MRI scanners, magnetic resonance imaging. It's all the same thing, right? This is the same physical basis no matter what we call it. But NMR really describes more of what is going on in the system. We've talked about nuclear magnetism. The R, right, resonance, has to do with the spin angular momentum of the particle, and it also has to do with what we're going to exploit to be able to cause this change in orientation of the magnetic field. And what we're ultimately trying to do here is to take the magnetization that is in the sample or the patient and have it change its orientation so it looks like that. So it's perpendicular to the applied magnetic field. Now, I want to sort of cut to the chase as to why we would even bother to do this, and then we're going to go back and understand a little bit about how it is that we do. So I said earlier that we generate some magnetization in our patient or sample by applying this external magnetic field. But if we want to go in and actually measure that we can't detect it simply because the externally applied magnetic field is so strong, right? That whatever amount of magnetization is there in the sample, our instrument that we would use to measure this with would be totally swamped. Right? Even if we went point by point and measured field strength, so within the patient there would be a little bit, more or less field strength than outside of the patient, but it would be such a tiny difference there would really be no way to detect it. Well, if I change the orientation of the magnetization inside the patient so that it's perpendicular to the applied magnetic field, what does it look like? This is now the net magnetization vector. I should have made it the same length. So it's the same magnitude, or it's supposed to be anyway. But what does it look like? Is it static, the way I've drawn it here? Well, what does it mean that I've rotated at 90 degrees? Well, what it means, we've said that if we think about a coordinate system in this scanner, right? We'll call this the z direction, we'll call this the y direction, and this one coming out at us the x direction. So the external magnetic field is applied along z. And the initial amount of magnetization that we detected here was parallel to that z direction. And we said that the way that we were able to do that is because each of the individual spins is precessing around the static magnetic field with random phase. So for each one of these guys, it has a transverse and longitudinal component vector. If there are millions of them and they all have random phase, their transverse components go away. They cancel out. And all we're left with is this longitudinal component. Well, what must be going on if we can generate this transverse component? That must be telling us the opposite, that of all of our millions of individual spins, that their longitudinal components have canceled out, yet they all have, or at least many of them, have enough coherent phase that their transverse components sum to something detectable. If that's the case, that this represents the sum of those transverse component vectors, well, think about one of these individual transverse component vectors. Individual proton, and we decompose it into its two component vectors. One is parallel to the applied magnetic field, and one is transverse or perpendicular. So this transverse component, what does it look like? The transverse component is actually rotating around the applied magnetic field at the Larmor frequency. That's where the precession comes from. Right? Remember, this is precession. So if we think about this is the net magnetization of this individual proton, we can decompose it into a longitudinal component which stands still and a transverse component which rotates around at that same Larmor frequency. And the vector sum of those is this precessing spin. So if we think about the entire sample, if all of the longitudinal components sum to 0 and we have coherent phase of these transverse components, that transverse component sum has to be precessing around the magnetic field at that Larmor frequency. Any questions about why that is? If this is important, so if that's not clear, I should go over it again. Everyone's okay? All right. So why do we care about that? And again, we're going to go back to how we do this in a minute, but I just want to get to the essence of why this is important. Remember, at rest, we couldn't detect this signal. But now all of a sudden, we have all of the magnetization of the sample rotating around the axis of this static magnetic field at a frequency of omega, whatever it is. At 1.5 Tesla, it's about 64 megahertz. So we now have a magnetic field that is rotating at a very high frequency around this static magnetic field. If I add something to our system here, I take a little coat hanger and I bend it into a loop and I hook it up to some little Radio Shack voltmeter. So every time that this magnetization moves past this loop of conductor, there's going to be a little deflection of the needle here. This is, right, Faraday's law of induction. Right? That a moving magnetic field will induce a voltage across a conductor. So all of a sudden, this magnetization, which is the same stuff that we couldn't detect before, just by changing the orientation, it now can be detected. So it's very important for us to be able to get to this point where we have rotated this magnetization so that it's perpendicular to the static magnetic field, and as a result, it is precessing. Now, if this were static, we wouldn't be able to detect it any better. If this were a static vector, then the net magnetization of the whole business would be the vector sum of this large externally applied magnetic field and this tiny little transverse component. It's simply the fact that there is something moving that allows us to detect it. And the amplitude of this change in voltage, right, is proportional to the magnitude of that transverse component magnetization. The bigger this vector, the bigger the induced voltage. The smaller this vector, the smaller the induced voltage. Now, the rate at which it is rotating or precessing is also essential, but that's not going to vary. That's a function of the static magnetic field strength. So if we think about perhaps different locations within the patient, and we're trying to compare the signal at those two locations, we're not going to get to the point of localizing things until tomorrow, but at these two locations, there might be a different amount of net magnetization. And when that net magnetization is turned so that it rotates through this plane that is perpendicular to the static magnetic field, it induces a voltage proportional to how much magnetization is there. So if we have a smaller amount over here and a larger amount over here, all of a sudden we can detect those two differences. Any questions about this? Right, so all of these terms, by the way, right, transverse magnetization, the signal intensity, right, all of you radiologists, you read out MR scans and you talk about the signal in the MR image, that's it. When you look at the grayscale image and it's whiter or darker, what you're looking at is how big is the transverse magnetization coming from the tissue represented by that little voxel in the image. Do you have a question?
Shouldn't it be a component of the vector? Why is the whole magnitude of the transverse equal to longitudinal?
Because I haven't told you how we do it yet. We're going to do that next, but we've taken the whole thing and rotated it.
With the intent.
So everything is now in the transverse plane. I'm going to talk next about how we get there. But I just want people to see where we're going with this, that this is how we generate these. So now we're into something real life, right? So this is the actual signal intensity that you see in your image is simply a measure of transverse magnetization. Okay? All right. So how do we do this then? Well, we've said previously that ultimately, whenever we're going to think about what's going on in our system, it has to do with the relative population of these energy states. Okay? That there is some relative filling of these energy states where the lower energy level predominates and the magnetization is completely random. Right? And then as we get to coherent longitudinal magnetization, that requires some input of energy, our static magnetic field. Eventually, we want to get to the point where we can generate this transverse magnetization. This is just another stop on this continuum. It means that we have to put more energy into this system, right? And drive the system even further towards a higher energy state. So, as I said before, no matter how strong you make the magnetic field, even though it's really not practical to be taking your static magnetic field and making it stronger and weaker and stronger and weaker, we really need another system for being able to get enough energy into this system to cause a change in the orientation of the magnetization. And it turns out that if it were just a matter of adding energy on the scale of what it takes to generate that initial net magnetization parallel to the static magnetic field, you would completely cook the patient or the sample before you would ever get to this point. And the way we're able to do this is by exploiting a principle called resonance. Okay? So resonance, the easiest way for us to understand this is, well, I think that the easiest example, the best example I have, I think is very dated. Probably no one here would remember this, but there was once upon a time, there was something called a cassette tape that was used. You guys remember those?
Yes.
Anyway, so, and there was a company called Memorex, which I think they still exist, but they made cassettes. Now they make CDs. So, and they had a famous television commercial where there was this woman named Ella Fitzgerald who would sing this really high-pitched note, and they would show a picture of a glass sitting on the other side of the room or stage or whatever it was, and she would sing out this really high, you know this one? She would sing out this high-pitched note, and the glass would shatter. So she didn't hit it with a hammer, she didn't touch it, it was just her voice. Or similarly, if, for example, if I take a tuning fork, right? I actually used to do a demonstration of this. So let's say I have a C tuning fork, and I have another C tuning fork, and then I have a, let's say, an E tuning fork. So everyone knows that the difference between the C and the E tuning fork, you hit it, and it makes a tone, and there'll be two different tones. You can use it to tune your guitar, or whatever you use it for. So if I have all of these in close proximity, and let's say I strike the first C tuning fork. So if these are close enough together, without touching, eventually the second C tuning fork will start to ring. And you can silence the first one, and you can actually hear the tone. On the other hand, even though the proximity, I didn't draw it right, but even though the proximity might be exactly the same, the E tuning fork will never start to ring in the presence of that ringing C tuning fork. And that is an example of resonance, right? That these tuning forks give you this reliable pitch because they have a natural frequency at which they oscillate. So when you perturb the system, right, hit it on the side of the table or your hand or whatever it is, it starts to oscillate at a predictable frequency, which is that note C or E or whatever Ella Fitzgerald sang. So given that these two have the same natural frequency, they both oscillate at exactly that same C note, they are able to, with extreme degrees of efficiency, transfer energy one onto the other. Whereas the same amount of energy has no effect on the E tuning fork. Right? And that is simply because we don't have the same resonance between C and E as we do between C and C. And this is true, you know, there are many examples of this in the natural world, including the precession of the protons in our sample, right, or any nuclei in an NMR experiment. That if we have our precessing proton, which is precessing at that Larmor frequency, and we can know and predict what that's going to be. Why? Because we know that we're dealing with protons, and we can go look up what the gyromagnetic ratio is. And we know the strength of the magnetic field that we've exposed this to. So we can actually compute what the precessional frequency of those spins is going to be. Okay? Given that we know what this natural frequency of those protons is, if we apply some energy at the same frequency, we should be able to get a dramatic transfer of energy onto that sample, right, without completely cooking it. So because we know this natural frequency, we can apply this energy at that Larmor frequency. What that means is that the energy which we supply has to be rotating or oscillating at the same frequency as these spins. So what we do is we think about our scanner. And this is the externally applied magnetic field. Our sample is in here, and it has some net magnetization. Well, I drew that backwards. That looks like this. And we want to put a lot of energy into this sample of spins so that we can get it to change its orientation. Okay? Well, the way we're going to do that is by turning on another magnetic field. And we will turn on this magnetic field perpendicular to the orientation of our previously applied magnetic field. And this is going to be called B1. This static magnetic field, by the way, is often called B0 or B0. So we turn on B1. Now, as I said before, if you just turn it on as a static magnetic field and leave it on, what's going to happen? Right? All that means is that the net static magnetic field seen by our sample is the vector sum of these two. Right? It would be something that looks like this. Right? This would be the result. That wouldn't do anything. It's just another static magnetic field. It would change the orientation of the sample slightly, but it doesn't have the effect of adding this additional energy to the system. And even though it changed the orientation of the sample slightly, it didn't do so by causing phase coherence of the transverse component magnetization. It only did that by causing the whole sample to change its orientation with respect to another static magnetic field. So instead, what we are going to do is turn on B1 for a period of time, and then we'll turn it on again in the opposite direction from which we turned it on the first time. So we can have this B1 turned on this way, and then have it turned on in this direction. And switch it back and forth at the Larmor frequency. So now what we have is a magnetic field, which in this example is oscillating. With the right hardware, we can actually make it continually rotate as if it's precessing. So we can actually have this magnetic field rotate through a plane perpendicular to B0 at this frequency. If we do so, then what happens is that we have a large amount of energy very efficiently transferred onto this system and drive it towards a higher energy configuration. One of the features of that higher energy configuration is this coherence of the transverse component magnetization. So what happens is that as we turn this on and leave it on, there is going to be a progressive rotation of the magnetization of our sample until it is perpendicular to the axis of B0. At this point, what this means is that there is an equal amount of those longitudinal component vectors pointing in each direction, and there is a high degree of phase coherence so that everything is precessing, right, through that transverse plane. And if we then set up our little antenna over here, we can detect a change in voltage, right, which is proportional to the magnitude of the transverse magnetization. And we can call that signal intensity. So by doing this, we've been able to generate some measurable signal from this magnetization that was in the sample. Any questions about how we do this? Now, in the example that I've shown you, we go from 0 coherent transverse magnetization to the point where everything is in the transverse plane. How do you know how to do that? We know what frequency we have to turn this on at, but let's think of it this way. Let's say I turn this on at the correct frequency, and I turn it on, and I immediately turn it off. What's going to happen? Well, again, we're talking about putting energy into this system to change the relative occupancy of those energy states. So the amount of energy that is added to the system will determine the extent to which this occurs. And it's a continuous process. So with a very small amount of energy added to the system, we will reduce the component magnetization in the longitudinal direction somewhat and generate some degree of phase coherence, meaning that the net magnetization might look like this after some period of time. Whereas if we leave this on long enough, we will eventually get to this point. So it's a matter of how long we leave this B1 in operation that determines how much we rotate the magnetic field. Okay? And the angle of rotation, right, this is sometimes called the flip angle. That might be a term that some of you have heard of, or the angle of nutation or rotation. That is determined by how long we leave this B1 on. In a situation where we only have one choice about the magnitude of B1, we could accomplish the same amount in a much shorter time simply by making B1 much stronger. Or it might take a lot longer if this were smaller, because it's a matter of the total amount of energy that we deposit in the patient. Now, in terms of energy deposition, one thing to just keep in mind, and we'll touch on this more later in the week, is that this component here is the biggest source of power deposition that leads to heating in MR, which is a very significant safety concern. And in fact, there is a term, which we'll talk about later on, called specific absorption rate, which describes the amount of energy in watts per kilogram that you are depositing in the patient, right, with a typical MR experiment. So cranking up this B1 to make it much stronger, leaving it on for a really long time, definitely have these effects on the magnetization, but what you are doing is putting a lot of energy into the patient. And depending on how you do this, there may be significant concerns with tissue heating that could potentially be a safety issue. So it's something to be aware of that we'll talk about later on. Now, the frequencies that we're talking about here, right, this omega at 1.5 Tesla, right, is around 64 megahertz. So when you guys, if you get in the car and you go home and you turn on some FM radio station, that will be in the frequencies that are on there, 90 something point whatever, is the units are megahertz. Okay, so this commonly is referred to as something that we call a radio frequency pulse, or RF, simply because the frequencies that we're using in MR at the types of field strengths at which we're usually imaging humans, around several Tesla, tend to be in this megahertz or radio range. So that's where this term comes from, pulse, simply because we turn this on for a brief period of time to cause this effect. Okay? So this RF pulse is what is going to generate our signal. So to review briefly, right, what we have now is that our patient is in the scanner. The first thing we need is a static magnetic field B naught to generate some amount of magnetization from the sample, but not something that we can detect. Okay. The next thing that we have to do is turn on B1, which will rotate at a frequency of omega naught, corresponding to whatever our field strength is and whatever nucleus we're interested in imaging. And that is going to cause a rotation of that magnetization if we apply the right amount and duration of this RF. Will give us 90 degrees of rotation. With 90 degrees of rotation, we have now, at this point in time, 0 detectable longitudinal magnetization. Why? Because the longitudinal magnetization of the individual spins is equally distributed in 2 directions so that they cancel out. Whereas we have a detectable but rotating transverse magnetization, because the transverse component of all those individual spins are precessing and they are in phase. Okay? So it's not the magnetization of individual spins that is changing. Not that we could detect it even if it was. It's not that the actual axis of the nuclear magnetism of an individual spin is changing its orientation. It's the net effect of the whole sample due to this input of energy. Now, the 90 degrees that I put in here is just because it's going to be convenient for us to deal with. And we'll talk on Wednesday morning about using different amounts of rotation of that magnetic field that may have specific benefits. But for our purposes now, just to keep things simple, we're going to talk specifically about what happens when we go to 90 degrees, where we have a maximal amount of transverse magnetization and no detectable longitudinal magnetization. That transverse magnetization, of course, is what we can detect as signal intensity. Okay? So now we can generate signal. The question that I want to ask you at this point is, we haven't made an image, so we don't know where this signal is coming from. But let's say if we go back to our same example, that we have our normal liver and our tumor that we're trying to discriminate. And let's just say that in terms of the spatial localization issue, I can take care of that. And I can give you a measure of signal from each of these places. Are you going to be able to tell the difference between those two? And if so, what's the physical basis for that difference in signal intensity? So I'll show you 2 signal measurements, one from the normal tissue and one from the abnormal tissue. Can you tell them apart based on what we've done so far? And if so, on what basis? What is it about those 2 pieces of tissue that differs that you can detect? Any ideas?
Like a different Lamore frequency, so they're at different MTs at the same time.
Okay, so that's an interesting idea. So you're saying, do they have different frequencies of precession? We're going to assume at this point, sorry about that, that we're going to assume that everything is seeing exactly the same magnetic field strength. Thanks. Everything is seeing exactly the same magnetic field strength. The Larmor frequency, can you guys see that? It's not a great color. that the Larmor frequency is a function of field strength and gyromagnetic ratio. Well, we're only talking about protons, so everything has the same gyromagnetic ratio. We're making an assumption, and this is an assumption, that the magnetic field strength B0 is exactly the same every place inside this scanner. Under those conditions, everything has the same frequency of precession. Okay? So, could we tell the difference? Okay, exactly. So, if we make an assumption, first of all, that I'm giving you two measures of signal, and that they each come from the same volume of tissue. So let's say I give you two measurements that each come from, 10 milliliters of normal liver and 10 milliliters of tumor. So the signal amplitude will probably be, right, higher in the tumor than it is in the normal liver tissue. And the simple reason for that is that the tumor likely, it would depend exactly on what it is, has a greater number of protons per unit volume, okay, or the so-called proton density of these two tissues is different. So based on this measurement, if we could localize it in space, we could detect a difference simply as a function of the fact that there are more or less protons in one of these than the other. Because ultimately, for a given volume of tissue, what determines the amplitude of the signal? Well, it's the vector sum of all of the protons in that sample. If I have a tissue where there are more protons crammed in to a fixed volume, and I have another tissue where there are fewer, we're going to detect different signal amplitudes. And that's really the only basis on which you could differentiate these two tissues at these points, is based on the fact that they each have a different number of protons.